20.3, Introduction to Mergesort. Now we start to learn Mergesort. First, so let's look at a simple problem. Our next problem, problem number 15. Merge two sorted arrays. Given two ordered arrays, we assume each one already sorted. The question, how to merge them to get an ordered array? Why we need to study this question first. Here, let me give you the motivation. Why we consider this problem. Because this is a fundamental problem that we can use to solve many other relatively more advanced problems. So let us look at a special situation. How to sort a huge array. We know how to sort an array, right? Have you thought about if this array size is really huge? So how big it is? Think about billions of data items or numbers. Billions, even trillions. So you can imagine. You cannot load all the data into your computer memory. When that happens, how do you sort the array? That special situation. It's rare, but sometimes you have to think about it. Here, so let me describe an idea to solve the problem like that. Suppose this line segment represents that huge array. Okay? Because it is so big, we cannot load it into memory at the same time, so we may like to use our divide and conquer approach. So we can divide into smaller pieces, right? So let's assume we divide it into many much smaller pieces. Then for each piece, then we have no problem to use our existing sorting algorithms to sort, right? So we can get each subarray sorted. Okay? And then we can even apply parallel computing. So multiprocessors, each processor we can do the sorting. So parallel computing. All right. Then after we get each one sorted, the next step, how do we combine all the sorted subarrays to get that large sorted array? Now we need to do the merge step. Now you need to merge two ordered arrays. If you can merge two ordered arrays, then you can merge 3, 4, 5, any number of ordered arrays. That's the motivation. All right. So let us study how to merge two sorted arrays. What is the fastest algorithm to merge two sorted arrays? All right. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements? In order to get a more efficient sorting algorithm for this question, one principle we need to have in our mind, that is take advantage of the structured data. We know the structured data is very valuable. If I recall that element uniqueness problem, in that one we sort the array first to make unstructured data to structured data. The first step. Then we can get better performance. Here, We do not need to do that step. We already have structured data, right? So we should take advantage of the structured data. Otherwise, so we waste a lot of useful information. So that's not good. Yeah. So the question is, how do we do it? Yeah. All right. So here we have several sorting algorithms at this point, right? Yeah. We need to use our experience. Yeah. All right. When we use our experience, we make selection in this way. Do not use any sort that does not make use of any order information. Some sorting algorithm never takes advantage of order information. That's not good for our current situation. Yeah. For example, selection sort. In selection sort, does it take advantage of the order information? No, because the best case, worst case, average case, all have the same number of comparisons. The order information does not improve the performance. Selection sort. Okay? Similarly, the bubble sort does not take advantage of the order information. Worst case, best case, average case, same number of comparisons. So we should not use, any of them, right? Yeah. Next, we have one that takes advantage of the order information. We just learned, insertion sort. Insertion sort, because the best case is really fast. The worst case, average case, pretty slow, but the best case, that corresponds to the ordered array, extremely fast. That is big theta of n, the fastest possible among all the sorts. Yeah. So that's the one we can use. Okay? Yeah. Remember, we have a application, I talk about a special kind of data which apply this insertion sort. So that is when we have the data almost sorted array. Only there are some scattered clusters, the data not ordered. In that situation, insertion sort should be used. But we have this conclusion, insertion sort is a good choice under our current situation. Next, we need to look at how to use the idea of the insertion sort to solve our current merging two ordered array problem. All right. We need to take a different view on insertion step. So let's start with the insertion step, but this time we need to, adjust our view a little bit. All right, so let's look at a typical insertion step. So let's go back to our old insertion step because we want to get a new idea from it. In order to, solve our current problem in a better way. All right, so let's look at this diagram. Insertion step. So one element V, we want to insert it into the current ordered array. So that's our insertion step. Now, can we modify this view a little bit to adapt it to our current problem, merging two ordered array, the current problem. So let me do this part in this way. We treat that single element, this V, as one element array. Can we do that? The array has only one element, right? Yeah. Extreme case, it is okay, right? All right. Then another extension, we treat it as a sorted array. One element, it is sorted. But also extreme case, sorted. So here, can we just treat that we just merge two sorted arrays, right? Yeah. So our new interpretation. Yeah. Two sorted arrays are combined or merged to get a new sorted array. So that's the new view. Yeah. And this new view connects to our insertion step. All right, so our new view merge two sorted arrays for a new sorted array. Now, although it is different from the insertion step, but you can see they are correlated. So we can borrow the insertion step to, implement our merge step. Yeah. In my next video, I will talk about that, the merge step, merge operation. You can see part of the merge step, very similar to our old insertion step. Yeah. All right, so next, we need to have a good discussion on this merge step. All right. When we apply the new merge view, we also look at the data size. Here, for this special case, the data size, there are k data items. First sorted array, but the second one, only one. Yeah. So this situation has some problem. We observe some problem here. So what's the problem? It is not balanced. The data distributed in two subarrays, not in a balanced way. So not a balanced way. Yeah. And we have the experience. If the data distribution is not in a balanced way, then we could have very poor overall performance. Poor, worst case, because we will have the, worst case situation. Poor overall performance. Yeah. So that's not good. So we don't like to see that. Yeah. So we want to improve the performance. And we want to avoid the worst case. Improve the performance. Yeah. Some principle we used before. Remember the fake coin problem. Think about the fake coin problem. In that one, we use some nice principle to get our data distributed in a balanced way. That's the balancing principle. Balancing principle. When we split our data into two subarrays, we should make the split in a balanced way. And in our binary search, we also use this balancing principle. So we split array right in the middle, the median, right? So then we drop one of the two subarrays. So you can see in many places, we use this balancing principle. Yeah. All right. So try to make two subarrays of equal size, as close as possible. So that's the way we do the divide step, divide and conquer. Divide step, we use this way. Yeah. All right, so that's our first introduction video. Yeah. All right, so let me stop here. Yeah.